Hello and welcome to this lecture series on microprocessor and microcontroller. And We are currently studying this 8085 microprocessor. This is video number 9, and the topic of today is input output device interfacing with timing diagrams in microprocessor 8085. In the last lecture, we covered the timing diagrams of 8085 microprocessor with respect to various commands. We have seen that timing diagrams are important and they give us an idea of how things are happening inside microprocessor. They have a mix of both information. They have the information of software as well as the hardware. From the software perspective, we know that which signal will be on or off under what circumstances. From the hardware perspective, we came to know which signal was triggered under what circumstances and in one particular t state when it was triggered, whether on rising edge or on a falling edge, or maybe on lower level or higher level of voltage. So we saw that information there, and we will see some more examples of that in our laboratory sessions. So let me just first show you the plan that we had initially, because I have made a minor change to that. So up till now in this microprocessor 8085 topic, we have covered introduction, programming model. We have also covered simple programs. We have covered architecture. We have covered pin diagram. Then we have covered interrupts, and then finally we saw machine cycle and T states, and also the timing diagrams in the last lecture. And as per the plan, this lecture that we are in currently should also uh, discuss the same issue of machine cycles and timing diagrams. But I feel sufficient details have been given in the previous lecture, and the remaining thing is of practice, which we will of course practice in the laboratory session. So input output with timing diagrams is the topic of today. But before beginning that, from the previous lecture, let me just bring that slide again here. If you see here, I have also written some special instructions here which consumes 6 T states for opcode fetch machine cycle. So if you see here, some of the instructions, they were having two kind of complete T states that they were trying to consume. So for example, if you see this call conditional statement, then it consumes 18T when the condition is true, and it consumes 9T states when the condition is false. So let me discuss this particular thing here, because there are a couple of more instructions which will have similar kind of t states. They will have a dual t state. I mean, sometimes they will be of 18 t states and sometimes they will consume only 90. A similar instruction is return conditional. So let me first tell you what call conditional statement is. Call conditional statement is like, it will just monitor the status of your flag register, and from there it will try to call a subroutine. For example, the normal call instruction is call, but call conditional statement is like CZ. CZ is a call conditional statement, one type of call conditional statement, where if zero flag is set, then the call will be made. So CZ means call when zero flag is set. And after that, you will be, of course, giving a 2 byte address of a memory location so that you can go to that particular memory location and execute the call there. And we are already aware of the fact that whenever we make a function call or a procedure call or a subroutine call or even an interrupt service routine call, what happens is the current contents of the program counter, they are kept onto the stack. So stack is also accessed in that. So assuming that we are executing a cz instruction, and the condition there happens to be true, that is zero flag is set, then what will happen, what t states will be consumed, let us discuss that. So of course, that cz, and then after that there is an address, so it will consume 3 bytes in the external memory where it is written. So first of all, we will be needing one opcode fetch cycle, and since this call conditional falls in this category, so it will be of 60 states. So after that, we will need two operand fetch cycles, because after cz instruction we will have a 2 bytes address. So that makes it 6 plus 2, that is 8 t states are consumed in that way. And when before jumping to that particular uh, means location where the subroutine is written, this will also access the stack, because they have to keep 2 bytes of data onto the stack. So for keeping that data onto the stack, we know that we have 2 bytes, and we have already used, 60 states for opcode fetch, and 3t states for 1 byte fetch, and another 3t states for another byte fetch. So 6, 7, 8, 9, 10, 11, 12. 12 t states have been consumed, and for putting data onto stack, we will need two memory write cycles, which will again consume 3 plus 3, that means 6 t states. So 12 plus 6 will be 18 in that particular case. So if the condition CZ means zero flag is set, so if the condition is true, that is zero flag is set, then CZ statement will consume 18 T states. However, if the condition is false, then what happens is you only just have to do the opcode fetch, which will be of 60 because it falls in this particular list. And after that, you have to read two operand fetch cycles, which will if the condition is false, I don't think that you will be needing to read both of the bytes, because after CZ there is a 2 byte address. So now this is only 60, and if the condition happens to be false, then in that case it won't be uh, performing this opcode fetch cycle. Other it will be doing this idle machine cycle, so 6 plus 3 will become 9, and that way only 9 t states will be consumed there. So there is no need of fetching this operand, because anyway the condition is true. What we will do with operand, so that way, it can take 18 or 90 states depending upon the status of zero flag if CZ statement is used. Like this, there are also statements or call statements based on parity and auxiliary carry and so on and so forth. Similarly, return conditional is also there. So there are a couple of more instructions which have this kind of behavior, which can take some amount of t cycles sometime and some other amount of cycles that time. So we have to keep that in mind, and the software that we are using, that is Jubin simulator, it will show it as 18t always, because it takes the maximum number of t states that this call instruction can have. So that's a glitch there, but since we are aware of this fact, we can make the adjustments accordingly, right? So this was some leftover topic from the previous lecture which we have covered. And now coming to today's topic, we are talking about how to interface your input output devices with your microprocessor. And in that context, I'm telling you that there are two ways in which it is done. First is called as input output mapped input output, and the second one is called as memory mapped input output. What do they mean? If an input output device is connected to locations which are not the memory locations, I mean, in 8085 we all know that there is a possibility of attaching 64 kilobyte of memory at max, right? You could use lower memory than that, and you could use full memory, that is 64 kilobyte memory. So in case if you are using a lower memory, I mean, suppose you are using only say um, 16 KB of memory. So the remaining memory that remains, those memory locations can be assigned to these input output devices. You can connect your input output devices there. So that way, if you are using the memory locations to connect the input output devices, then that would be called as memory mapped input output. However, if you are using dedicated addresses which are dedicated for input output, in that case, it will be called as input output mapped input output. So in case of memory mapped input output, the instructions that you were using for data transfer to and from memory were like STA, LDA, or maybe you were using the HL register as pointer. So you were using this LDA command, and you were supplying some address. So those all commands will be valid. Means input output devices will be treated like memory elements only, because anyway they have been connected to memory locations. So those memory instructions will be sufficient to deal with those. However, if you talk about this input output mapped input output scheme, in that there are two separate instructions, in and out, which will be used to transfer the data. So we will see uh, that in programming also in today's session. But before that, let me just ask this question. This is the architecture of 8086 microprocessor, sorry, 8085 microprocessor. And you know that to connect the memory, you have got only this address lines and data lines which are multiplexed for the lower order byte, right? So assuming that you are using full 64 kilobyte external memory, these lines will be completely busy, right? These lines will be completely busy. So where will you put the additional input output devices? Because in 8085, this is also one of the points to note that 256 total input output devices can be connected. This is like asking in your modern days computers, how many pen drives can you connect by using your USB hub? You can connect one USB hub to your USB port, and that USB hub can be further connected to another USB hub at one of the USB ports, and that way you can make millions of devices connected to your computer. But is there a maximum limit to that? Yes, there is a maximum limit for every computer depending upon its architecture. So here also you can see that 8085 allows you to connect a maximum of 256 input output devices whose port addresses will be again from 00 to FFH, right? Because if you are trying to connect 256 devices, you can just represent them by using the numbers from 0 to 255. So the port addresses will be in that range only, right? But where will you connect them is the question. If full memory has been used, then where will you connect them? So it's not that if you are using this address and data bus to connect to memory, then these lines will not be available. It is the same as saying that if in your house you have got an electrical connection from where suppose you are that electrical connection goes to your tube light, and after that tube you only have one tube light in your house, assuming that you have only one tube light in your house and you bring some new tube light. So can you not use the same connection to connect that new tube light just by taking wires from that in series or parallel connection? Yes, it can be done. So similarly, this address and data bus wires are available, which they are coming out of microprocessor, and they can be connected to various things in various types of connections. So that's what we are going to see today for connecting the input output devices in the two modes, that is the input output mapped input output or the memory mapped input output, right? So memory mapped input output does not requires a separate discussion, because we already know that whatever is the memory location, if you are using a memory which is lower than 64 kilobytes, then for the remaining addresses you can connect input output devices there, right? So the primarily we are going to discuss the input output mapped input output, and then in the end we will make a comparison between the two schemes, right? So let me just move forward and show you this diagram. So this is the circuit diagram to interface a input port. I mean, you are trying to interface a input port, right? And in this particular figure, we have assumed that the input port has an address of 80 in hexadecimal. 80H. So that's what we have assumed, right? So for that, this circuit is made. So now we will discuss everything in this circuit one by one. But before that, let me also tell you, when the microprocessor is trying to deal with an input output device in input output mapped input output mode, in that case, your address bus and data bus, I mean, the address bus is of 16 bits and the data bus is the lower byte of that 16-bit address bus. So from A0 to, that is from AD0 to AD7, you will have the port number which is there for addressing the particular input output device, because you can have at max 256 input output devices. So the content on AD0 to AD7 will be exactly same as the content on AD8 to AD15, means on the address lines, the lower and higher byte will remain same always, right? So in the beginning, as we have seen in the timing diagrams also, when we float address through the microprocessor on the address lines, so if you are dealing with the input output mapped input output scheme, in that case the address will be duplicated on the lower and higher order byte, because anyway the maximum address can be 255. That is, if you start from 0, it can go up to 255. So the address on lower and higher order byte will be the same. ALE will work accordingly, but then since the address is available on both, we might use the higher order address bytes to take address, because after the ALE has been disabled, the data will be available on the AD0 to AD15 pins. Sorry, AD0 to AD7 pins. That is the lower 8 bits of that particular address bus. So that is one fact, that is address lines are duplicated byte by byte when we deal with input output devices in IO mapped scheme. So considering that in mind, and also keeping the fact in mind that we are taking an example where the address of the where the address of the input port is 80H, that means 80H. So we are taking that address and we are trying to interface a device from where we are trying to take some input. So this is the device that we have connected. This device is just like, if you will close any of these switches, then accordingly that value will become high and you will have some 1010 combination here. And this is a tri-stated buffer. Through this buffer IC, we are trying to read that data that we have received from here onto this particular data bus of the 8085 microprocessor. So this is the internal data bus of 8085 microprocessor, and we are trying to connect it to a input device. I mean, this device will be giving you some data to read, right? So we are taking it through a buffer, but the activation of that buffer will depend on this particular logic. This activation will depend upon the logic that is being shown here. Now, you see that this is a buffer IC and it is a active, means you can enable it by putting a zero signal here, because this is an active load device. So if you put a zero here, this will be activated. So the data bus is directly connected to it. So the moment this is active, this buffer is active, the data from this will be transferred to this data bus. If this is not active, you keep whatever data you want to put here, it will not be transferred to that side, right? So to activate it, we are using the addresses, right? So for using the addresses, we have connected our address pins here, A0, A1, A2, A3, A4, A5, A6, and A7. And they have been connected to this decoder. This decoder will give you this Y0 signal as low when this Y0 signal will be low when this address becomes equal to 80H, 80 in hexadecimal. So this logic that you see here is applied only for 80 address in hexadecimal. So how that logic works, so we will see that a little later, but let us first look at this small circuitry. I mean this particular leg of this OR gate. Let us look at it. If you want to activate this IC, if you want to activate this particular buffer, you have to supply a zero signal here, right? So if you want to have a zero signal here, both of them should be simultaneously zero, because this is an OR gate. If any one of them becomes one, then you will be getting a 1 at the output. So we don't want that. So when both of them are simultaneously 0, in that case only this buffer will be activated. So to make this thing as 0, what do we need? Uh, if you want the output at this point to be 0, these two should be 0. These two should be 0 means this signal should be 0. I mean this read bar signal should be 0. That means read is activated. And if you look at this particular signal, if this is 0, that means this is 1. If this is 1, that means input output is activated. So input output signal is activated. That means microprocessor is trying to deal with an input output device, and read bar signal is 0. That means read is also activated because it's an active low signal. So in that case only this upper limb of this OR gate will become 0, and we want the second one also to be 0. So this signal you need to be 0. So when will this be 0? So this is a decoder which is 74LS138 decoder. So I will just show you working of this decoder, although it is not a part of our syllabus. You must have learned it in your digital logic course. But just to give you a quick review, let me just show you the structure of that 74LS138 IC. So this is again a decoder, and you can see that the inputs are address input pin A, B, C, and then you have got enable pins. There are three enable pins. Two of them they are active low, and one of them is active high. So there are only six inputs that you see here, and apart from that, there is this ground pin and one output pin on this left hand side. So and if you see there is this VCC and then you have y0 to y6 output pins here, means pins number 0 to 6 here, pin number 7 output is here. This is ground, this is VCC. Now what do we want? We want the signal at this particular pin. Why not? We want the signal as this particular pin to become 0. So whenever this signal will be 0, as we have seen in this particular circuit, this logic will also be 0. So 0 and 0 will make it a 0, and this decoder will be activated. So that's what we want. So without giving you the internal details of how this IC is constructed and what is the purpose, let me just show you the truth table of that. So the signals that you see here, G2A, G2B, and G1, they are represented by this E1, E2, E3. This is G2A bar, G2B bar, and this is G. So they are represented by this and this A0, A1, and A2. You can see that these A0, A1, and A2 are these pins, ABC pins, or you can see it in the IC also. These are these ABC pins. And this G2A bar, G2B bar, and G1, these pins are E1, E2, and E3 pins. And on the output side, you can see that you have got bits from Y0 to Y7. And what do we want? We simply want that this Y0 should be equal to low. So if this is low, then what should be the value of E1, E2, and E3? So you can see that all of them are low except this E3 bit, that is G. So you need only this G as 1, and rest everything should be 0. I mean, this should be 0. For this to be 0, all of these three should be equal to 0, and for everything else is also 0. So this is 1 and then 7 times 0. So you can imagine 1 7 times 0, that is the binary equivalent of hexadecimal number 80. So if 80, we take the hexadecimal, if we take the binary equivalent, it will become 1 and 7 zeros after that. So you can see that this circuit is a perfectly valid circuit for 80H. If you put and if the address will be 80H, in only that case this Y0 will go low. And if the device intends to read an input output device, it will apply the appropriate signals and this particular thing will be activated. Once this is activated, the data from these lines can be transferred to this particular data bus of 8085, and that way you will be able to read the input from this particular device, right? So on the address lines, you can see that these address lines could be, actually you can also take it from, instead of taking from A0 to A7, you could also use A8 to A15, because there the address will be available forever. But since they have taken A0 to A7, their circuit have been dependent on address latch enable signal, so that when you try to transfer data, then this combination will become of data and this circuit will be automatically deactivated. So both ways it can be used, and that is how you take inputs from the input port. So in this way, you can still you have to make various different circuits for attaching various different devices to this 8085 microprocessor. At max, you can attach 256 number of devices, but usually for as input devices, as in the current scenario, if you see your own computer, how many input devices do you connect to your computer? One keyboard is there, then of course one mouse is there. So these are the input devices that you connect to your computer through buffer. So your keyboard has a buffer. When you type, that the keys that you press, they are stored in that buffer, and then that buffer is fast enough to transfer the data to the internal bus of the computer. So this can be thought of as keyboard, and this is the buffer for the keyboard, and this is the internal data lines of your keyboard. If you have ever seen your laptop getting repaired, when you take out your keyboard, you take out the pin of that complete keyboard out also, so that pin is connected to actually the data line somehow of your computer. So this is the same scenario, but this is a very old computer, so data lines are perfectly visible here, right? So this is how you take input in the input output mapped scheme, right? So I will talk about the programming part of this later, but let me first discuss this output. How do we deal with the output, right? So in this case, we are assuming that our 81H is the address. Instead of 80H, our address is 81H for the output device. Because we have connected input device at 80H, now let us connect the output device as 81H. This address can be any address of your choice, and for that matters, you can again see here that the circuitry is like this. This is an output device, And in this particular microprocessor, we have set LEDs. So you can see that Q0 to Q7, there will be 8 total outputs here, and these 8 total outputs will be connected to 8 different LEDs. The dotted symbol here, it simply means that there are 8 LEDs which are connected, and you want to give some output to this. So data bus of microprocessor, data bus of 8085 microprocessor is attached here, and this is a latch. So whenever this latch will be enabled, or whenever this buffer latch will be enabled, the data bus, whatever value it has, 0101 format, it will be transferred to these particular LEDs, and accordingly for 0 they will be off, and 1 they will be 1. So this is like the screen of your computer. However, in microprocessor 8085, we have 7 segment display, or maybe this LED blinking display from where you can read it in binary. So this kind of displays are there. When I will show you the actual kit in the laboratory, you will appreciate this fact. So now again, this circuit that you see here is assembled according to this address 81H. We want this thing to be activated only when this address appears here. So I guess the logic for this address you can see in the truth table and make out. So this is what we mean by giving an output to this complete thing, this 885 microprocessor. So from the data bus, the output will be transferred. So this is how we take input and output devices. And now let me list some differences. Let me list some differences between memory mapped and input output mapped input output, right? So let me read it line by line, and let us discuss these facts. So in memory mapped input output, in this device, the address is of 16 bits. Of course, because you're trying to connect your input output device at a vacant location in memory where you haven't inserted the memory chip, so the address has to be of 16 bit. Thus, the A0 to A15 lines are used to generate device address. This is very, very obvious. And the equivalent point in input output mapped input output is in this device, the address is of 8 bits. Wait a minute, let me check if my lecture is getting recorded or not. Yeah, it is getting recorded. Yeah, because it would be scary if I'll keep on recording for an hour and later I realize that it is not recorded. So yeah, in input output mapped input output, the device address is of 8 bits, and we all know this because 256 maximum devices can be connected to this 885 microprocessor through input output mapped scheme, and A0 to A7 or A8 to A15 lines are used to generate the device address. And we have discussed this, that A0 to A7 is a mirror image of is an exact replica, not mirror image. A0 to A7 is the exact replica of A0 to A15 in the first clock cycle, when the addresses are floated over the address buses. So that is also possible here. Now, memory read and memory write control signals are used to control read and write input output operations here. And here the corresponding operations will be input output read and input output write. So this is again very obvious thing. Now this is an important thing. In memory mapped input output, if an input output device is connected, which commands will you use to transfer data to that? LDA, STA, LDAX, STAX, move, move, add, and CMP. So these commands will be used. These commands are the same commands that you were using to deal with the externally interfaced memory. But since you have connected your input output device in that address space only, that is why the same commands will work there, right? However, for input output mapped input output scheme, instructions available are only in and out. So in and out instructions are only available for that programming, right? So let us now see a program for this particular thing. Let us now make a program which shows you the usage of this in and out command. So I'm just opening this again, Zubin's 885 simulator, and let's see a program for that. So I've already made the program. Let me load the file for you. So this is your program number 16. Let me autocorrect it so that it becomes nicely indented, and let me assemble it. So this is assembled. So let us first see the program. The program is very simple. Again, you have two assembler directives that lets the assembler know that we are trying to store our program from 7500 hexadecimal location in the memory, and we are trying to execute it from there itself. So begin signifies the start address of execution, and org 75000 signifies the start address of storing the hexadecimal equivalents of these particular codes, right? So here what happens is, if you see this devices tab, if you see these devices tab, you can see that from 00 to FF, you can see that here it is F and here it is F0, so this address is FF. So these are total 256 lines where your input output devices can be connected. You can get it to the devices tab. This is the memory tab, which was very huge. If you load the entire memory, that memory is completely very huge because there were 64 kilobytes of locations. However, in the devices tab, you only have 256 such locations. In the memory tab, if you had to edit any memory, you have to go to this show the loaded memory location, and there you can put your address here, and you can put your content of memory there, so it will be automatically uploaded. But if you show the entire memory, you cannot just double click here and change that, right? So in the devices tab, however, you can just directly edit it. For example, if I keep some data at this ninth location, let me keep a data, say 40 here, 40 in hexadecimal. So whatever you enter here will be entered in hexadecimal. So in the ninth location, I am putting a 40 here, and since it has been put in the devices tab, this means that a device has been connected whose address becomes 00. I mean, sorry, whose address becomes 09 only, because you can have only an address of 2 hexadecimal digits or 1 byte, right? So I want to load this data into accumulator. So there is very simple command in 09, and you can put H here also. So in 09 and H, it is by default in H. In this particular process, in this particular software, it is by default in H. In GNU 8086, it was, if you skip the H, it will be taken as a decimal number. However, by default, it is H. So if you put H here or do not put H here, it is one and the same thing. But if you want to make it in decimal, then you have to put a D specifically here, right? So now, what do I want to do? At position number 9, data of 40 hexadecimal is kept. I want to take it as input inside accumulator of microprocessor. So the command is very simple. In, and an address you have given is for the input output port, which is 09H. So 40 will be loaded into your accumulator, right? Then what you will do is, since accumulator now has this 40H, you will keep that data in L register for usage of it sometime later. Now you will keep some another data in A, which is 03H, and you would like to output it at 20H location. I mean 20 is this location, 20 and 0, this is location 20. So I want to see this data uh, of 03 at 20H. So this data is kept in accumulator register, and from that accumulator register, I want to move it to the externally interfaced input output device, which is connected at this particular address 20, right? So let us just assemble this program and execute it. So it is already assembled. This is in this particular tab. I have already put this data of 40 here. So let us assemble it. The moment I will run this program for the first time, you will see that this data of 40 will appear in this register section in the accumulator. So let me begin executing it by pressing Alt and right key. So you can see that data of 40 has come into the accumulator. So it is as easy as this, right? So the data of 40 has come into the accumulator from this devices tab where you had this 40 connected at location 0009. So let me further execute it. So now L contains 40 also. You can see it here because the data that I have received in this, I'm keeping it in some safe register, or even I can keep this data of 40 in your externally interfaced memory so that it can be used later. So you can keep that data safe for whatever purpose you want. Now let me again execute the next instruction. So A will contain now 03. I want to put this 03 at memory location 20. So the next statement will do that. So now this has been executed out 20, and let's see the devices tab. So at location number 20, this 03H is present, right? So out 20 statement is there, and in the accumulator, the data was 03. So that data has been moved to this particular location 20. So this is how you give output to devices in input output mapped input output scheme. And then simply you have halted your system. So that's how you deal with input output devices in 8085 if they are mapped in input output mapped input output scheme. Otherwise, if they are mapped in memory interfaced scheme, then you don't have to do anything much, because anyway they can be dealt with the commands of memory only. So this is how you will program it there. Let me not save it. Yeah. So this is how you do that. Now coming back to the differences that we were discussing. Hmm. So coming back to the differences that we were discussing, we have seen this, how instructions that in and out are used for taking input and output from 8085 microprocessor in input-output mapped input-output scheme. Now coming to the next point, data transfer is between any register and input-output device in this memory mapped input-output scheme. Of course, inside microprocessor you have got registers, and this input output device is connected in the address map of this memory unit. So data transfer will be from register to device on, and in this case data transfer is between the accumulator and input output device. This is also an important point, because in this in and out command you can only use accumulator to transfer the data in between, right? So for input output devices which are connected in this IO mapped IO mode, you only have your accumulator register for data transfer. However, here in this previous case of memory mapped input output, you can use commands like MOV, then you can specify some, maybe no, you can use these commands like st uh, stax. So stax command will use it will transfer the contents of accumulator to that particular memory location. Or you can use hl register prs pointer, where the data will be kept in m register, and the moment you update that m register through hl register prs pointer, if that is pointed to that particular input output device, it will be moved. So m register can also be used there. Similarly, there are commands which can transfer data by using any register like B register, C register, etc. to memory locations. And we have seen that in our laboratory sessions. So that flexibility is given here. From any register, you can transfer the data between input-output device, but in this scheme, you only have you the accumulator register which will be able to transfer the data. And maximum number of input-output devices are 65536 theoretically. This is very important. If you do not use memory in your 8085 system, how will you run programs? So you need to have at least some memory, so that where you can put your programs and execute them. So the theoretical maximum input output devices that you connect is 65536. However, this is not possible, because if you will not give some location to memory interfacing, then you won't be able to run your programs, build your stack, and use these commands. So theoretically, there is a possibility of attaching this much devices, but nothing will work if you attach this much devices in your system. Or maybe these devices then have to behave as absolute memory locations. Then maximum number of input output devices are 256. That is what we have already discussed, that through this input output mapped IO scheme you can only have 256 maximum devices, and their port numbers are from 00 to FF in hexadecimal number system. Execution speed using LDA, STA, move instructions is there. Execution speed using LDA address, STA address is 13T and 70 states for move instructions. However, the execution speed here is only 10T states. Okay, so let me also show you the T states for this particular input and output thing. So I close that program. I have to open that again. Yeah, so let us discuss the input output and their corresponding timing diagrams. So let me load that code again. This is the code. Let me assemble it. It is assembled. And let us say we want to see this t states of input. So it is clearly written 10 and output 10. So 10 fixed states are there. So let us see what those states are for this input command. So for input command, you have this opcode fetch. Of course, opcode fetch will be there. In will be taking 1 byte, and your this thing, I mean the address that you have given, it will also take 1 byte. So opcode fetch is there, then there will be an operand fetch which they have given as memory read cycle, and we have discussed the reasons for this, because technically they are both same. You are reading things from memory, so they have written opcode fetches memory read cycle only. And if you move forward after this, if you move forward, uh, Let me just, so opcode fetch cycle is there. Then after opcode fetch cycle, there is a memory read cycle. Memory read cycle because you want to read 1 byte of memory for that. Then there is a input output read cycle. Why? Because after this opcode has been fetched and operand has also been fetched, you would like to read the input output device if you are using the in command. So that input output is also used, and I guess it will also take three t states because we have discussed that. So this is also again taking your three t states. So a total of I mean 4 plus 3 plus 3. So you have got 10 t states here. Similarly, if you see it for the out command, I guess it will also be the same. In place of input output read, there will be input output write only, right? So let me show it for input command only, and let us see what operations are there. Is it similar to reading the memory? So you see at the beginning of the cycle, in the same way we used it for memory, we have this opcode fetch cycle, because here we are reading the memory only, actual memory only. And similarly, this portion will also remain the same. Let us see this portion where we are actually dealing with the input output device by writing some data into it. So here you can see that port address 75 is mentioned. Here also the port address 75 in hexadecimal is mentioned. And you know these the both are same, because I told you that address and this data bus will have the same content, and ALE has become equal to 1. So address has been lashed, and you can see that here this has become 1. That means input output device has been activated in this input output read cycle. Earlier it was not activated because you were reading the code from memory, so up till now this was not activated. Then for read, you made the signal low because this is an active low signal. So in that way, input output read cycle can also be made. And again, for reading the input data buffer, you have input data 6F, you have this, I mean, starting from this half location of T2 and it continues to half location of T3. So this is same as the case that we had for here, right? So in this way, you can draw, I think, timing diagrams for any circuit now. If you see two, three more such timing diagrams for different instructions, you will get an idea of what is going on. So in this way, you can draw these timing cycles also. So now coming to the next point. Yeah, so execution speed is 10t states. So this is also clear to us from our thought process, as well as we have confirmed it from the timing diagrams of that. Now, decoding 16-bit address may require more hardware. So of course, this is true. When you have a 16-bit address, more amount of hardware will be required to decode that, and maybe more multiplexers are required to connect various devices. And those multiplexers are now called as USB hubs if you're talking only about USB devices, right? And decoding of 8-bit will require less hardware. So this is a general comparison between memory mapped input output and input output mapped input output. So this is how you try to attach your input output devices here and deal with them. So I guess things have been clear to you. We have seen a new thing today. We have seen this devices tab where only 256 devices can be externally connected. So I guess this is it for this particular lecture, and in the next lecture we are going to start the addressing modes and instruction set. So it is not possible for us to cover each and every individual instruction in detail, because we have 74 such instructions and there will be 246 patterns of them, and some of the instructions will be setting or resetting some kind of flags, and there are some special conditions with every instruction. So what we will do is I will just give you a general overview of the complete instruction set, and we will discuss the important instruction sets there. So I guess this is it for this particular lecture, and I'll be seeing you in the next video. Thank you very much.